My name is Ramana. I teach in the School of Public Policy and Global Affairs at the University of British Columbia in Vancouver. And it's always hard coming after a series of speakers because they tell you everything that you want to speak about. So I'm just going to sort of reinforce some things that they mentioned and elaborate a little bit on that. And I'll sort of broadly make 3 points. So the first I want to say is, if somebody from the nuclear industry were here, they would say, these people are all talking about these old kinds of reactors. Now we have this new generation of reactors. They're not going to have any of these problems. They're going to be perfect, et cetera, et cetera. And they use all these, terms like, advanced nuclear reactors and small modular reactors and so on. And, if you look at the, details of these designs, there's not a lot that's actually new about these. I mean, most of these reactor designs go back to the 1940s and 50s and the sort of, when there was expectation that nuclear energy was going to grow so fast and most of our electricity should have been now from nuclear reactors had you gone back to the 1950s. And so during that period, there were a very large number of nuclear reactor designs that were explored. I mean, Sharon sort of mentioned the Army's own nuclear power projects, which sort of explored a bunch of designs, but there were a whole bunch of others as well. And some of these were built at that time, and others were not even built. And those that were built, they found lots of problems with it. In particular, the 4 main kinds of designs that we talk about in case of small modular reactors and so-called advanced reactors are either the light water reactors, which are the common ones, or water-cooled reactors in general. I come from Canada, where we use heavy water, not light water. Anyway, so the water-cooled reactors. There are fast neutron reactors that Ed spoke about, high-temperature gas-cooled reactors that also Ed mentioned, and there are the so-called molten salt reactors. Right? And this is sort of, broadly speaking, the 4 categories. I mean, there are some variations of that. And all of these had been tried. And there's a reason why we have a lot of light water reactors and none of these other reactors, because they all had problems with them. And I can sort of talk about what these problems were. But in most of these cases, the issue was that the utilities realized that it wouldn't make sense to operate them and make money off it. So, for example, the last high-temperature gas-cooled reactor that was built in the United States was in Fort St. Vrain in Colorado. And it basically ran for about 7 years, if I remember right. I don't remember the exact number of years, but it was in the 1970s and 80s. And the utility decided to shut it down when they had some kind of a problem. It had operated with a load factor of around 15%, roughly speaking. And when the utility decided to shut it down, the New York Times actually carried a headline which said, "The world's safest reactor is closing because it rarely runs." And that was very, very typical of that kind of reactors. And that's why many of these designs are not there. But what we are seeing with all these so-called small modular reactors, advanced reactors, is, if there's a nuclear engineering professor and they have like a few $100,000 in grant money, they can hire a few graduate students and they will go off and do some research into one of these old designs and then modify it a little bit, use a new alloy for this, use a slightly different design for the steam generator, and lo and behold, you have a new reactor design. So one of the designs that was mentioned here, Oklo, the company Oklo, the people who founded Oklo were graduate students in MIT when they started this whole design. And there was another student at the same time at MIT, Leslie Dewan, who had an idea for another reactor design that was supposed to be the greatest whatever thing, till one of the professors actually looked into the details and said it doesn't actually do what it's supposed to be saying. So all that is to basically say there's a lot of hype here, and if you look behind, it's not really valid. And sort of digging a little bit deeper, the second point I want to make is that if you look at what a nuclear reactor designer would like to do, they're in designing a new reactor, they have some goals or some priorities, if you like. Typically, they talk about 4 main priorities. So one is the fact that you don't want to have severe accidents. You want to lower the risk of accidents. And so you want to make your reactor design safer. A second goal might be that you want to make it cheaper. Joe talked about the costs of these reactors, and so you would like to make your nuclear reactor cheaper in a way. A third is, Sharon Squassoni talked about the risk of proliferation, and different designs have different kinds of pathways to proliferation, increase the risk or lower the risk depending on the kind of design choices that are made. So that's another priority. And the last, which I don't think anybody mentioned so far, is the challenge of dealing with radioactive wastes. We still don't have a demonstrated way of safely dealing with this. And the best that the nuclear industry has come up with is to essentially dig a deep hole somewhere, bury it, and hope and pray that it never comes out. They won't call it that way. They will say, oh, we have a geological repository and there are engineered barriers and so on. But in plain language, that's what it means. And so all of these are priorities. So some nuclear designs, for example, pride themselves on the fact that they produce less radioactive waste, right? So that's also another kind of priority. Many years ago, my former colleague Zia Mian and I looked at a whole bunch of small modular reactor designs, and we observed something which is kind of obvious in hindsight, which is that no single design can actually optimize for all these different priorities. And if you try to make a design that does one of these priorities better, it'll do bad in the other priority. So to give an example, if you wanted to design a nuclear reactor that produces less radioactive waste, then you have to operate the reactor in what's called the fast spectrum, meaning that you don't slow down the neutrons that are emitted by the fission process, and these fast neutrons then go on to triggering other fission reactions. And which means that you have to have the reactor be much more concentrated in space. It has to have a lot more fissile material, enriched uranium or plutonium, packed together inside the core of the reactor with no moderator inside that. So it's a very concentrated source of heat, which means that then one thing you have to do is you cannot use water to cool it. That's why they use molten sodium or other kinds of metals. But the other thing that it means is that you have to have a lot more fissile material, a lot more plutonium or enriched uranium inside the core of the reactor. Therefore, this becomes more proliferation prone, because a country that imports this reactor, if they, without operating the reactor, just siphon off some of this plutonium or enriched uranium, they can process it and then hopefully produce a weapon with that. So there is always going to be this kind of trade-off between these different things. In particular, when you go to small reactors, small meaning less than 300 megawatts, then you lose out on what are called economies of scale, which is that if you want to build a reactor that produces 5 times as much electricity, you don't need 5 times as much concrete or 5 times as many workers, and therefore the cost per unit of power capacity or electrical energy generated becomes higher for a small modular reactor. And this is amply shown in the experiences we've had so far. The last thing I want to mention is the discussion about AI, and I think it was Joe who rightly mentioned that the time scales that we are talking about just don't meet the time scales at which this AI before the AI bubble bursts that they're going to need. But the other thing I want to mention is, if you want to understand how something works and why something is working, you also need to follow the money, right? This is the standard sort of advice given to any journalist, if you like. And so if you look at what's happening here in the AI, all these big tech companies making all these announcements, there are sort of 3 kinds. They all talk about, we are investing in nuclear power, that's why don't worry about emissions and so on and so forth. But if you dig deeper, you find there are sort of 3 kinds of nuclear projects they talk about. The first is, I'm done. The first is there are some where they are trying to revive an old nuclear reactor like 3 Mile Island or Palisades. And there are obvious safety risks there. I'm not going to talk about that, but that's one kind of process. The second is that they get into a contract with some operating nuclear plants with some utility company, and they basically siphon away electricity that formerly were supplied to consumers. So that's another way they can get some nuclear power. And the third, of course, is they make announcements about all kinds of small modular reactors and advanced reactors and so on. And if you read those press releases, most of the time they don't tell you anything about how much they're going to spend. But when they do say, what you see is that they often are spending. They're committing a few hundreds of millions of dollars. The highest number I've seen is from a consortium that involves NVIDIA and a bunch of other investors, saying they're going to invest $650 million. And of course, we don't read the fine print in the contracts. I'm sure they have smart lawyers who have all kinds of conditions before which they're going to spend this money. But compare that $650 million or $500 million from an Amazon consortium with the cost of even the cheapest small modular reactor design that we have talked about so far, which is the NuScale design, the UAMPS project in Idaho. The final cost estimate was $9.3 billion for just 460 megawatts. Okay? Neither does the 460 megawatts match up with the energy demands of these data centers, nor does the cost match up with the few hundreds of millions of dollars. So the way I'd like to interpret it is these companies are spending this, are talking about this money and using not their energy budget, but their PR budget. And why are they doing this? Because I think one of the things they must have seen a few years ago was a lot of talk about cryptocurrency companies and Bitcoin and the amount of emissions from that. And it was a lot of bad press for the cryptocurrency industry, to the point that government started regulating it. Even the Biden administration had regulations on it. China actually banned Bitcoin mining. And so this, for my opinion, this is what they're thinking about. Oh, we should get ahead of this whole negative publicity by saying, don't worry about emissions. We are investing in small modular reactors. But it's not going to amount to anything there. I'll stop there. Thank you.